All right, just want to do a quick walkthrough of the Quizizz review. Take a look at some of the answers and the rationale behind them. So, starting with number one, true or false, an object with only one force acting on it can be in a state of equilibrium. That is false, because with only one force, by definition, you have an unbalanced force. There's nothing else to balance it out, so there is a net force, which means you can't be in equilibrium. Equilibrium means all the forces add to zero, which can't happen if you only have one force. A force of 8 newtons is applied to a crate so that it slides across the floor at a constant velocity. That's important. That means we are in equilibrium. The velocity itself doesn't actually matter. As long as we're in equilibrium, the net force, regardless of any of this information, has to be zero. The net force is always zero if an object is in equilibrium. A force of 8 newtons is applied to a crate so that it slides across the floor at a constant velocity. Again, 1.5 meters per second. What is the magnitude of the frictional force? Well, if we had an 8 Newton applied force, then it has to be balanced by an 8 Newton frictional force. That allows us to be in equilibrium. Those two forces have to add up to zero, so friction has to be equivalent to the applied force. Is it possible for the object in the diagram to be moving to the right and have this free body diagram? You can see you have a normal force up, force of gravity down. Yeah, absolutely. This thing could be moving along with constant velocity. It has no forces in the x and y direction, but it could definitely be moving at a constant velocity in equilibrium. So yes, it is possible. It could be moving at a constant velocity. Technically, I mean, yes, the forces weren't drawn in. It just means the diagram is wrong. So that's not really the best answer. Sure, it could be doing anything if the diagram's wrong. Forces cause motion. Kind of tricky. You got to be real careful with the wording here. Motion. Do we need to have a force for something to be moving? No, we don't. Something could be moving at constant velocity without any force. That's inertia. So we don't need a force for motion to exist. So net forces, nope. Motion can occur when there is no net force. That is true. Forces cause acceleration. Now, that is sort of true, but it's not just any force. Applying a single force doesn't guarantee that you get acceleration, because that force could be balanced out by friction or something else. So really, friction only occurs when there's acceleration only occurs when there's a net force. So we need a net force. We got to be careful, very careful with the wording here. So net forces cause acceleration. A single force may or may not cause an acceleration because it could be counteracted by another. So a tennis ball is thrown upward by a student so that it leaves their hand at 5.29 meters per second. After it leaves their hand, what keeps it moving up? Nothing really. The ball has inertia, so it is in motion. It has a tendency to stay in motion. And in fact, the ball's slowing down because gravity would be pulling down on it. A forward force of 15 newtons is counteracted by a backward friction of 6 newtons. Mass of the object is 2 kilograms. What's the acceleration? Well, what's the net force? If 15 is being counteracted by 6, 15 minus 6, that's 9 newtons. Force is m over it. Force is mass times acceleration, so acceleration would be force over mass, or 9 newtons over 2 kilograms. That would give us 4.5 meters per second squared. This is kind of a funny way of writing meters per second squared, but it would be in the direction of the larger force. And it would be 4.5 meters per second squared. I was hoping that would go away. Your mother is standing on a concrete floor in flat shoes. When she lifts one foot, what happens to the normal force? Nothing. Normal force does not change. Her entire weight is still supported by the floor, so the floor still has to push up on her with her entire weight. So normal force doesn't change there. If the sum of all forces acting on a moving object is zero, the object will, if the sum of the forces acting on is zero, that means the object is in equilibrium, and that means that it will continue with constant velocity. So if it's already moving at a certain velocity, it's going to stay at that velocity. If it's sitting still with a velocity of zero, it's going to remain sitting still. Which object has the most inertia? Okay, this is a really easy one. Don't get carried away with all these numbers they're giving you. Inertia. Mass is a measure of inertia. The thing with the biggest mass has the most inertia. It has nothing to do with whether an object is moving or sitting still. Inertia is mass. Mass is inertia. So objects that are sitting still have just as much inertia as the same object of the same mass that's moving. Block of weight W is pulled along a horizontal surface at a constant speed V by force F, which acts at an angle theta, with the horizontal as shown. A little bit difficult to see. Just blow that one up. There we go. It's a block sliding across the floor. We got an applied force on an angle. So what that means is, can't draw on that. Let's try, oops. Let's see here. There we go. What that means is there's a normal force that's up, there's the weight which is down, and then some part of that applied force is also up. It's, part of it's to the right, part of it's up. So there's two forces balancing out the weight, which means the normal force doesn't have to carry the entire weight. So the normal force is greater than 0, but it's less than the entire weight. It's definitely not equal to the weight because it's being helped by another force, and it's not greater than the weight because that other force is helping. An object sliding across a surface will experience blank friction. If it's sliding, well, that means it's moving, and then we're talking about kinetic friction. No problem there. The Earth pulls downward on a ping pong ball with a force of 1 Newton. If this is the action force, which is the reaction force, we're talking about Newton's third law force pairs here. And if the Earth pulls down on the ball, well, then the ball exerts a 1 Newton force on the Earth. That is the equal and opposite force. Given the free body diagram, which of the following must be true? Let me blow that up. Normal force up, gravity down, friction to the left. So our options, the box must be accelerating to the right, and it wouldn't be accelerating because there's no net force to the right to cause it to accelerate to the right. This is definitely possible, so this guy isn't right. The friction force must be accelerating the system to the left. That is true, right? We're going to have an acceleration to the left. And this says the box must be moving to the right. That's also true. For there to be a friction force to the left, without any other applied force, then the box must be moving to the right. So we actually have 2 right answers there. I think, see if I changed that. I believe I changed it to choose to. Yeah, it's choose to. So 2 things, 2 things are true there. Acceleration is to the left, which means it's slowing down as it moves to the right. What coefficient of static friction? What is the coefficient of static friction if it takes 44 newtons of horizontal force to move a box that weighs 86 newtons across a horizontal surface? So horizontal surface, the normal force is the weight, which is 86 newtons, and we're saying we need to apply a force of 44, which means we need to overcome a friction force of 44 newtons, and then mu, of course, is the ratio of the friction force to the normal force, and in this case we're given numbers, so 44 over 86, and that works out to be 0.51 if I'm not mistaken. 80 kilogram skydiver is free falling at a constant velocity. That's the most important part. Doesn't matter what that constant velocity is. If the velocity is constant, it's not changing, then the acceleration is 0, which means the net force, the total force acting on this skydiver, must be 0. That's the only way you can be in equilibrium. Man on a scale notices the scale reads 40 newtons less than his normal weight. Which type of movement of the elevator could cause this greater than normal reading? That doesn't make sense. I think we got a mistake there. The man on the scale, if the scale reads less, then we can't really call it a greater than normal reading. So we're going to go with it reads less. If it reads less, then he must be accelerating downward. Let me make sure that's the answer. So I apologize. There's a mistake in there. It needs to get fixed. Yeah, accelerating downward. So it was meant to be less, not greater. Then we got one with some more numbers to it. A man, 80 kilogram man, standing in an elevator. The elevator rises with an acceleration of 2.5 meters per second squared. The force exerted by the elevator on the man will be, who knows? Well, 80 kilogram man, that's an 800 Newton man. And since we're accelerating up, we know it's got to be more than 800 Newton, so we got 2 options here. let's do a little math. I'm going to sheet over to here. Our free body diagram, we'll just call that the man. We'll call that mg, his weight, and we'll call this the normal force of the elevator, which is also his apparent weight. So we're looking for apparent weight here. Sum of the forces has to be equal to ma. We said that a was the 2.5 meters per second squared upwards. Sum of the forces in this case is the normal force up minus mg down, and we kind of get the familiar result that the normal force is going to be equal to m times a plus g over here. So we put some numbers to that. 80 kilograms times 2.5 meters per second squared plus 10 meters per second squared. Then we got a normal force or an apparent weight of 80 times 12.5, which is 1,000 newtons. All right. So 1,000 newtons is the answer over here. Whoops. There we go. 1,000 newtons. A man with a mass of, a mass of 15 kilograms is acted on by two forces, one of which is 15 newtons due east, while a second is 10 newtons due north. The acceleration of the mass is, we got to do a little math. Well, let's see. Oops. We need to do that. All right, we said 15 due east, so we've got a force here of 15 east. And we've got 10 north, so that's 10 newtons north. And this is, let's get the units in there, 15 newtons east. So we're going to have a net force, and the acceleration will be in the direction of the net force. It'll be proportional to the net force. The net force in this case, we're just finding the hypotenuse of this triangle. So the force is going to be the square root of the sum of the squares of the sides squared. So 10 squared plus 15 squared. We're going to take the square root. I'm going to do that right now. 15 squared plus 10 squared, 325, and the square root of that is 18.03. Well, if that's my net force, then my acceleration must be my net force over my mass. We said it was a 15 kilogram mass, so we're looking at 18.03 newtons divided by 15 kilograms. And I get 1.20. So if we go look at our answers, there is only one answer that has 1.2. If we wanted to go further and find the direction, that would be easy enough to do. We're looking at this angle, and of course the inverse tangent, or rather that angle would be equal to the inverse tangent of the opposite over adjacent. So the inverse tangent of 10 over 15 would be that angle. And I get, let's see, inverse tangent, 10 divided by 13, 37.6. Ooh, so I don't agree with their angle. That's terrible. Oh, no, I put the wrong numbers in. Try that again. Tangent of 10 divided by 15, not 13. I'd put a 13 in there. 33.7. All right, so I do agree. But as soon as you got the force in this case, or as soon as you got the force and divided by the mass and found the acceleration of 1.2, you're kind of home free. Force accelerates an object of mass m. Same force applied to a second body produces half the acceleration. What is the mass of the second body? Well, if it accelerates half as fast, that must be because it's twice as massive. So 2m, twice as massive. This is assuming that the force, the applied force, is the only force acting on it. And since you're not told otherwise, I guess you just have to assume that. 5 kilogram object and a 10 kilogram object collide. Which object receives more force during the collision? Kind of a trick question. This is a Newton's third law pair. If they smash into each other, though one object will put, object A will put a certain force on object B, and an equal and opposite force will be applied back to object A by object B. So same amount of force. That's Newton's third law. Magnitudes of forces are measured in newtons. A newton is, of course, a kilogram meters per second squared. That's why when we multiply m and g, m's in kilograms, g is in meters per second squared, we get newtons. Which diagram would provide the largest f sub y, the largest vertical component? Well, the tallest one, so that looks like diagram C. There we go. Which would provide the largest f sub x, or horizontal component, would be the longest one horizontally. So this guy right here, diagram A. Acceleration produced by a net force on an object is, well, let's take a look, inversely proportional to the mass of the object. That is true. As the mass goes up, the acceleration will go down. So that's true. Directly proportional to the magnitude of the net force. That would mean that as the net force goes up, so does the acceleration. That is also true. In the same direction as the net force. A third thing that's true. So all of these are true. We got a wooden box pushed across a rough surface with a constant speed of 2 meters per second. Which statement is correct? Take a quick look at that picture. There it is. Box, pushing force. Not a very exciting picture. The friction force decreases as the block slows down. That's not true at all. Once something's sliding, that sliding friction force mu Fn doesn't change. So once it's moving, that's just a constant friction force. The friction force increases as the block speeds up. Not true. Friction force doesn't change with speed. The friction force is less than the pushing force. What are we told here? Constant speed. So that means we are in equilibrium. So that can't be true. And finally, the friction force is equal to the pushing force. That is true. That's got to be true to create that equilibrium where the box does not speed up or slow down. What would be the acceleration of the object if it had a mass of 10 kilograms? We need to take a closer look there. The object has two forces on it, 30 to the left, 25 to the right. So the net force of 5 newtons. And we're saying pretend it weighs. So acceleration is F over M. We're saying pretend it weighs or has a mass of 10 kilograms. So 5 newtons over 10 kilograms, that's half a meter per second squared. And that's right there. An inertial reference frame is one in which, of course, inertial reference frames are ones where Newton's first law describes the motion of matter. Newton's laws work. There's a great deal of matter that doesn't matter. The object of interest is traveling in a circular path. That doesn't matter. The law of inertia is not applicable. That's the opposite of the answer. So, all right. And then finally, you're riding an elevator that is in motion. Using a spring balance calibrated in newtons, you notice that a 10 kilogram hanging mass reads 120 newtons on the scale. I feel like we had a homework problem with these numbers. What is the acceleration of the elevator? We're going to assume G is 9.8 in this case. And we're going to do the math. Let's go figure it out. We could probably get this by process of elimination or pretty close, but got a 10 kilogram object that has an apparent weight of 120 newtons. So on a spring scale, so we've got a tension force essentially, not that it matters. The answer is going to come out the same way. We've got mg, but we were told to use 9.8. So that is a mass of 10 times 9.8 gives me 98 newtons down. And we have to find out what the acceleration is. So sum of the forces always equal to ma. Sum of the forces, as usual, is that upward force minus the weight. And we know the mass, so we're going to find the acceleration to be the force of tension, which we know. We were told the force of tension is the apparent weight. We were told that was 120 newtons. So 120 minus 98, we want to divide that by the mass, which is 10 kilograms. So that's 22 newtons over 10 kilograms, and that would give me 2.2 meters per second squared. So back to the multiple choice here, 2.2 meters per second squared. And if I'm seeing more than my actual weight, then I must be accelerating upwards. So we've got the force required to keep this weight at a constant velocity, and that would be 100 newtons plus 20 newtons more to achieve that upwards acceleration. All right, that's it. If you have any questions, let me know. Hope that helps. See you soon.